Hello and welcome. I'm truly glad you found your way here to this quiet corner of the night. However you arrived, whether by chance, by curiosity, or by a simple need for a moment of peace, you are welcome. Perhaps you're lying in bed, the lights dimmed, the weight of the day slowly lifting from your shoulders. Maybe you're on a couch, wrapped in a blanket, the world outside hushed and still. Wherever you are, whatever your day has held, this space is for you. I've crafted it with care, a gentle pocket in the fabric of the night where wonder and calm can sit side by side, where the frantic pace of life gives way to the slow, deep rhythms of the universe. Tonight, we are going to wander together, not in a rush, not with the frantic energy of a textbook or a lecture, but slowly, thoughtfully, as two friends might while gazing up at a star-filled sky. We're going to let our minds drift into one of the universe's most profound and beautiful mysteries, black holes. And more than that, we're going to explore a cosmic ballet, a question that tickles the edge of physics and philosophy alike. Can two black holes, these titans of gravity, find each other in the void and become one? Before we begin, I should let you know that I've done my very best to make this story as soothing and sleepy as possible. The tone is soft, the pace is gentle. But, well, black holes have a way of captivating the mind. They are just too fascinating, too strange, too deeply wondrous to be entirely contained. So if, as we wander, you find your mind sparking with curiosity, wide awake with amazement, don't worry. It will settle again eventually, a little wiser, a little more connected to the cosmos, and ready for a rest that feels earned. If you're already enjoying this quiet moment, I'd be deeply grateful if you gave the story a gentle like, a small signal in the vast digital night. And if you'd like to join me for more of these sleepy journeys through science, consider subscribing. It helps other quiet minds find their way here. And if you're listening from somewhere special, a mountaintop, a bustling city, a small town, or just your favorite, well-worn chair, I'd love to hear about it in the comments. There's a special kind of magic in watching the map of our listeners light up, a constellation of shared curiosity across the globe. A quick, soft word before we begin. Like all stories here, this is a space for relaxation and education. It is a peaceful place to let your mind float, to wonder, and to learn. It is not, however, a replacement for professional medical advice or treatment for sleep disorders. Think of this as a lullaby for the curious mind. So now let's begin. Find a comfortable position. Let your body grow heavy, supported by the earth beneath you. Take a slow, deep breath in, and let it out, releasing any tension you might be holding. And if you feel comfortable, close your eyes. Look up, not with your physical eyes, but with the eye of your mind. Picture the night sky stretching out above you, vast and ancient and full of silent questions. The cosmos above you is not empty. It is alive. You can't hear it, but if you listen with your imagination, you might sense the faint, steady hum of existence itself. The resonance of spinning stars, the whisper of expanding space, the memory of ancient cataclysms. You can't see it, but the space between the stars is not a true void. It is a dynamic fabric, alive with gravity, movement, and history. The stars you picture aren't just random dots of light. They are messengers from the past, each one a faithful letter written in the language of photons, dispatched years, decades, centuries, even millennia ago, just to meet your eyes, or your mind's eye, tonight. The star you imagine now, shining so brightly in your thoughts, may have died long ago, its fiery engine extinguished in a final, dramatic act. And yet, here its light remains, a final, brave letter from a distant past, arriving late but still brimming with meaning, a testament to a life once lived. And in between those stars, in the deep, dark spaces where your eyes might first see nothing, something else waits. Something profound. Black holes. You won't see them, They don't send light your way. They don't sparkle or shine. They are the antithesis of light, the ultimate introverts of the cosmos. They move with a violent grace, hiding in plain sight, yet they are there, scattered like secret punctuation marks in the grand, run-on sentence of the universe. They are the periods, the ellipses, the enigmatic exclamation points that give structure to the story of gravity. What exactly are they? A black hole isn't really a thing, not in the way a planet or a star is a thing. It is, more accurately, a place where gravity has won the ultimate victory. Imagine taking something incredibly heavy, the mass of a giant star or more, and compressing it into an impossibly small point. The gravity becomes so intense, so overwhelming, that not even light, the fastest traveler in the known universe, can achieve escape velocity. That's the essence of a black hole. It's not a hole in the ground. It's a region of space where the very concepts of in and out are rewritten. It's a domain where time and light and matter fall inexorably inward, and nothing at all returns. They are born from death and transformation. Some stars, the most massive ones, live fast and furious lives, burning through their nuclear fuel in a cosmic blaze of glory. When that fuel is exhausted, the outward pressure that has sustained them for millions of years vanishes. And gravity, always patient, always waiting, seizes its moment. The star collapses under its own immense weight. Not all stellar deaths are so dramatic. Smaller stars, like our Sun, will end their lives more gently, becoming a dense, Earth-sized ember known as a white dwarf. Slightly larger stars might collapse further, crushing atoms together to form a neutron star. A city-sized object so dense that a single teaspoonful would weigh billions of tons. But if the dying star is truly massive, 20, 30, or more times the mass of our Sun, the collapse doesn't stop there. There is no force in the universe strong enough to resist. The core falls inward, beyond the state of atoms, beyond protons and neutrons, beyond any form of matter we can comfortably imagine. Collapses beyond light, beyond time itself. And what remains? Not a fiery core, not a glowing ember, but an absence. A silence wrapped in gravity. A black hole. Right now, as you breathe slowly and deeply in your quiet room, there may be dozens, hundreds, even thousands of these dark giants drifting through our galaxy alone. They are the ghosts of dead stars. They might have passed through whole star systems without causing a ripple, their gravity a gentle but persistent tug on the cosmos. They might be pulling subtly on distant planets you will never see, their presence felt only in the precise mathematics of orbital mechanics. But what if I told you that sometimes, in the vast, seemingly empty expanse of space, these silent giants find one another? In the immense cosmic ocean where distances are so vast that things appear frozen in time, black holes do move. They drift. They are carried by the currents of the galaxy, and they circle, they orbit. And when two black holes come close enough, the story of the universe adds a new, extraordinary chapter. It doesn't happen quickly. It doesn't happen suddenly. It unfolds over millions, even billions of years. It begins with a dance. At first, the dance is impossibly slow. Their immense gravitational fields reach out across the light years, intertwining like invisible hands. They begin to orbit around a shared center of gravity, like ghostly partners waltzing in the absolute dark. There is no music, only the silent, elegant geometry of curved space. They spiral closer and closer, a cosmic courtship conducted in perfect silence. Yet they are not entirely mute. They speak in a language more fundamental than sound, sending out invisible ripples in the very fabric of reality. These ripples travel outward through the substrate of the universe itself. They are not made of light or matter. They are gravitational waves. You can imagine it like this. If space were a soft, perfectly stretched fabric, like a vast sheet of silk held taut, Then two black holes moving in their orbit would tug and tremble that fabric. With every swing, every rotation, they would send out pulses, tiny stretches and compressions that carry the story of their motion across the universe. Those waves don't shake your body or rattle your chair. They are far too subtle for that. But they are passing through you right here, right now. If you could feel them, they would be like the faintest heartbeat of the cosmos, a vibration beneath all matter, a rhythm older than time itself. Eventually, as they lose energy through these waves, their orbit tightens. The dance accelerates. The black holes fall inward toward each other faster and faster, their paths tightening into a final, furious spiral until they merge, fusing into one larger black hole with a final, silent roar of energy. A release that cannot be seen or heard, only felt in the silent, stretching shiver of space-time. But we will get to that. Tonight is about beginnings. It's about stillness. It's about lying beneath the infinite sky and remembering that even in the cold, hard logic of science, there are stories unfolding of breathtaking beauty and profound slowness. Perhaps the most beautiful part of this story is the timescale. Black holes don't rush. They move with the slowness of deep time, where 1,000 years is merely the first hesitant note in a long, patient, cosmic song. The universe is not in a hurry, and tonight neither are you. So as you drift, know this: somewhere, far away, in the darkness between the stars, two invisible giants may be circling each other. They are not fighting. They are not chasing. They are not enemies. They are simply moving, slowly, quietly, drawn together by something ancient and inevitable. A pull as old as the stars, as fundamental as existence. You don't need to understand every detail of the general theory of relativity to feel the poetry in that. It's a story written in gravity. Just breathe. Let your thoughts drift with them. Let your mind move like starlight. Slow, weightless, and free. And as we rest in this quiet knowing, a new question forms, gentle yet persistent, waiting just beyond the horizon of our thoughts. What is a black hole, really? Let's float there next. So, what is a black hole, really? You've heard the name. It likely conjures an image. A swirling, fiery tunnel. A hole ripped in space, perhaps a portal to another dimension. Popular culture has painted them as cosmic vacuum cleaners, ravenous monsters roaming the galaxy. But a black hole isn't a hole at all, not like the ones you dig in the soil or find in a sweater. It's not empty. It's not even dark in the way the night is dark. The darkness of a black hole is an absolute, a negation. A black hole is gravity. Pure, undiluted, intense gravity. Gravity so strong that it has overcome every other force in nature. It is a place where the gravitational pull is so overwhelming that the escape velocity, the speed you would need to travel to break free, exceeds the speed of light. And since nothing in the universe can travel faster than light, nothing can escape. It is a one-way street in the cosmos, a door that only swings inward. To truly understand where black holes come from, we must begin with their opposites. Stars. Not the tiny, twinkling dots you see with your eyes, but the massive, ancient nuclear furnaces they truly are. Stars are the crucibles of the universe, and their life cycles hold the key to understanding these dark ghosts. Stars are born in majestic clouds of cold gas and dust, mostly hydrogen, drifting in the quiet, dark nebulae of space. For eons, these clouds drift, formless. Then, a trigger, perhaps the shock wave from a nearby supernova, causes a slight gathering. A clump forms, and gravity, the quiet architect, begins its work, pulls more and more gas inward. The cloud contracts, tightens, and as it does, it heats up. The pressure at its core becomes immense, crushing. At a certain critical point, the temperature and pressure become so great that hydrogen atoms, which normally repel each other, are forced together. They fuse, creating helium and releasing a staggering amount of energy in the process. This is nuclear fusion, the engine of a star. For most of a star's life, a perfect, delicate balance holds. The tremendous inward pull of gravity is perfectly counteracted by the furious outward push of energy from fusion. It is a stable, beautiful dance of pressure and light that can last for billions of years. But nothing lasts forever. Eventually, the star begins to run low on hydrogen fuel. Fusion slows. The balance, held so perfectly for so long, begins to tip. And gravity, always patient, always waiting, begins to win. The end depends on the star's size. In smaller stars, like our Sun, this collapse is relatively gentle. The outer layers are puffed away into space, forming a beautiful planetary nebula, while the core settles down as a hot, dense, Earth-sized cinder, a white dwarf. It will glow with residual heat for billions of years before fading to a cold, black dwarf. In larger stars, the end is far more dramatic. As they fuse heavier and heavier elements in their cores, they build a layered structure like an onion. When they finally create iron, the party stops. Iron fusion doesn't release energy. It consumes it. Suddenly, the star's core has no energy to push back against gravity. The balance shatters catastrophically. In a moment so brief, so final, the core caves in. In less than a second, a core larger than our entire sun can collapse into a sphere just a few dozen kilometers across. Atoms are crushed. Electrons are smashed into protons, forming neutrons. The core becomes an impossibly dense neutron star. The outer layers of the star, with nothing to support them, come crashing down at a significant fraction of the speed of light, only to rebound off the incredibly hard neutron core in the most violent explosion in the universe. A supernova. For a few weeks, this single dying star can outshine its entire galaxy. A last, defiant blaze of glory. But if the collapsing core is too massive, if it's over about 2 or 3 times the mass of our sun, even the neutrons cannot withstand the crush. There is no known force that can stop the collapse. It continues inward, beyond resistance, beyond matter, beyond physics as we know it. And a black hole is born. It doesn't explode into existence. It doesn't announce itself with a flash. It simply becomes a region of space where the escape velocity is greater than the speed of light. Point of no return. But here is the truly strange part. The black hole itself, the thing we talk about, has no surface, no solid crust, no glowing shell. There is just a boundary, a theoretical membrane called the event horizon. This is the point of no return. It's not a physical barrier. You wouldn't bump into it. It is a gravitational threshold. Once something, a particle of dust, a photon of light, an entire spaceship, crosses that invisible line, it can never come back. Not light, not time, not you, not even a single whisper of information can get out. Inside the event horizon, everything falls toward the center, toward what physicists call a singularity. This is the heart of the black hole, the point where all the collapsed mass is theorized to reside. It is a place of infinite density, where the volume is zero and the rules of physics as we know them quietly dissolve. Our equations break down here. The concepts of space and time lose their meaning. It is the ultimate unknown. It sounds scary, doesn't? An infinite point of destruction, a cosmic shredder. But it's crucial to understand that a black hole is not violent by nature. It doesn't actively suck things in like a vacuum cleaner. Its gravity is just like the gravity of any other object, only unimaginably stronger and more concentrated. If you could, by some magic, replace our sun with a black hole of exactly the same mass, nothing would happen to Earth's orbit. We would continue to circle that point of darkness just as calmly as we circle the sun now. It would, of course, be much darker and much, much colder, but we would not be sucked in. You could, in theory, fly a spaceship very close to a black hole, and as long as you stayed outside its event horizon, you could feel its immense pull, but you could still fire your engines and escape. No instant doom from afar. Black holes are quiet. They are still. They are patient. They don't chase. They wait. Now, here's something else to wonder about, something that bends the mind as much as it bends space. Time itself behaves differently near a black hole. Imagine a thought experiment. You are floating in a spaceship near a black hole, and you have a friend stationed far away, in a region of weak gravity. You are both holding identical, super-accurate clocks. You have a video link between you. From your perspective, hovering near the black hole, your clock ticks perfectly normally. 1 second, then another. Your heartbeat feels normal. Your speech sounds normal. Everything seems fine. But your friend, watching you through the video link, sees something profoundly strange. Your clock appears to be ticking slower than theirs. Your movements seem sluggish, as if you are moving through invisible syrup. Your voice is stretched out, deeper, slower. The light from your ship is redder, dimmer. From their point of view, time for you is passing more slowly. This is not science fiction. This is a very real effect predicted by Einstein's theory of general relativity, called gravitational time dilation. The stronger the gravity, the slower time passes. It's a confirmed fact. Right now, even here on Earth, your feet experience time just a tiny, tiny fraction of a second slower than your head, because they are slightly closer to Earth's gravitational source. GPS satellites in orbit have to constantly correct their clocks for this effect. If they didn't, the GPS on your phone would lead you astray within minutes. Near a black hole, this effect is extreme. If you were to hover just above the event horizon, and you could look back at your friend, you might witness thousands, even millions of years pass in their world in what felt like only a few minutes for you. You could watch civilizations rise and fall in fast forward. That's the strange magic of black holes. They don't just bend space, they bend time. They fold the fabric of reality itself. You may be wondering, if light can't escape, if they are truly black, how do we even know they exist? How can we study what we cannot see? The answer is we don't see the holes themselves. We see their footprints. We see their influence on the world around them. We see stars orbiting nothing. In the center of our galaxy, astronomers have tracked stars like one called S2, whipping around an invisible point at speeds of thousands of kilometers per second, following a perfect elliptical orbit dictated by an invisible object with a mass of over 4 million suns. The only thing that can be that massive, that compact, and that dark is a supermassive black hole. We see gas swirling in. Before matter crosses the event horizon, it often forms a vast, flat, spinning structure called an accretion disk. As the gas spirals inward, compressed and heated by friction to temperatures of millions of degrees, it glows fiercely, emitting torrents of X-rays. We see that brilliant, final glow before the plunge into darkness. We see light bending around them, an effect called gravitational lensing. A black hole's gravity acts like a cosmic lens, warping the light from stars and galaxies behind it, creating distorted, multiple images, or beautiful, perfect rings of light known as Einstein rings. And sometimes we even see a shadow. In 2019, the Event Horizon Telescope, a global network of radio observatories working in concert, achieved the extraordinary. It produced the first ever image of a black hole's boundary. The image showed a fiery, lopsided ring of light, the photon ring, surrounding a dark central region. That darkness was the black hole's shadow, the silhouette of its event horizon, the closest we can ever come to seeing a black hole. We see how black holes shape entire galaxies, how they anchor the vast, swirling arms of stars, how they quietly sculpt the universe from the inside out. They are not monsters. They are more like librarians, the quiet keepers of endings. They gather matter, hold it tightly, and wait. But even these endings have a deep, resonant beauty, because black holes are part of the great life cycle of the universe. Stars are born, stars live, stars die, and sometimes, from that brilliant, fiery death, a black hole is born. Then that black hole waits and watches, a dark seed in the cosmic garden, and perhaps someday it finds another. And when two black holes meet, something extraordinary happens. They don't collide like rocks or crash like cars. They spiral together in a slow, inevitable gravitational embrace. Their gravity intertwines, their event horizons stretch toward each other, and they merge, not explosively, but powerfully, invisibly. The energy of their union is released not as light, but as the most powerful ripples in the fabric of space itself. Gravitational waves. In the next chapter, we will float gently into that strange and wonderful idea. What is gravity, really? What does it mean to feel a pull, even when nothing touches you? What quiet force is holding your body to the bed right now and calling black holes into one another's arms? Close your eyes. Breathe in, breathe out. The dance has just begun. As you lie still, breathing softly in the quiet of your room, gravity is with you. It is the most constant companion of your life, yet so effortless that you rarely give it a thought. It's not loud. It doesn't buzz like electricity or hum like a machine. It doesn't knock or shout. It is a constant, invisible hand, pressing you gently but firmly into your mattress, cradling your weight, holding you close to the earth as if to whisper, "Stay." And so you do. You don't have to think about it. Your body knows this force intimately. It shaped you before you were born, telling your cells how to arrange themselves in a world of constant, gentle pull. This same force moves through you every second of your existence. It tells the oceans where to swell and recede. It holds the moon in its eternal, looping dance around our world. It guides the stars in their burning paths and gathers galaxies into vast, spinning pinwheels. Gravity is quiet, but it is not weak. In fact, it is the reason there are stars at all. It is the reason anything exists in the form that it does. Without gravity to pull the primordial gas of the early universe together, there would be no stars, no planets, no ingredients for life. It is the great sculptor of the cosmos. Let's float into that idea for a while, softly, slowly, as the night deepens around you. Imagine the universe long, long ago, before galaxies, before planets, before the first star ever burst into light. Just vast, dark clouds of hydrogen and helium, cold, scattered, and still. A profound silence, a cosmic waiting. Then, in that deep quiet, a slight gathering begins. A barely there clumping of matter, a drifting of atoms into slightly denser patches. Gravity, patient beyond all human comprehension, begins its work. It doesn't rush. It has no need to. It possesses an infinite patience, operating on timescales longer than mountains, older than oceans. Over millions of years, these tiny clumps grow. Their own gravity pulls more matter toward them. They tighten, they condense. As the pressure builds in their cores, heat begins to rise. The chaos of countless atoms crashing together drives the temperature up, and up, and up, until a magical threshold is crossed. Suddenly, nuclear fusion ignites. In a flash that ends the cosmic dark age, light bursts into the universe. The first stars are born. And all of this is gravity's doing. The softest force, the most gentle of pulls, is the one that births the most ferocious fire. But what is gravity, really? For centuries, the brilliant mind of Isaac Newton gave us our first true understanding. He saw it as a force, an invisible attraction between any two objects with mass. His equations were magnificent, predicting the orbits of planets with stunning accuracy. They still work perfectly for sending probes to Mars. He imagined it as a pull across space, an instant, mysterious connection. But he himself was troubled by the how. How could the sun reach out across 93 million miles of empty space and pull the Earth? What was the mechanism? It wasn't until Albert Einstein that a new, breathtaking picture emerged. His insight was one of the greatest leaps of imagination in human history. He proposed that gravity is not a force pulling across space. Gravity is the shape of space itself. And to understand this, we need a new metaphor. Close your eyes and picture space again. But this time, don't picture emptiness. Picture it as a soft, invisible, three-dimensional fabric. A vast, endless quilt, stretched taut in every direction. This fabric is space-time, a single entity combining the three dimensions of space with the one dimension of time. Now, place something with mass on this fabric. A star, a planet, a bowling ball. The fabric curves beneath it, dimpling just a little. This curvature is gravity. Now roll a smaller marble nearby. Instead of traveling in a straight line, the marble will curve inward, following the slope created by the heavier object. It wasn't pulled by a mysterious force. It was simply following the path laid out by the curved landscape. The larger object said, "Here is the shape of the world around me." And space-time replied, "And here is the path you must follow." This is the heart of Einstein's general theory of relativity. Mass tells space-time how to curve, and curved space-time tells mass how to move. That's why the moon orbits the Earth. It's not being yanked by an invisible rope. It's moving in a curved path, a straight line in the curved geometry around our planet, held in place by the shape of the world's presence. It's like a marble swirling around a funnel. The funnel's shape is what guides the marble's path. And that is why black holes are so profoundly strange. They aren't just heavy objects sitting on the fabric. They are punctures in it. They create deep, steep, bottomless wells in space-time. Their gravity is so extreme that the fabric of space curves all the way back onto itself, creating a slope so steep that even light, trying to climb out, simply slides back down. Their gravity isn't just strong. It is an extreme, inescapable geometry. You, right now, are held in that geometry. The Earth presses into the space-time around it, and space-time curves softly around you. That's why you feel weight. It's not because something is pushing down on you from above. It's because the space you are in is gently guiding you toward the planet's center, and the atoms in your body and the floor beneath you are electrically resisting that fall. When you drop something, a pen, a pillow, a wandering thought, you are watching it fall along the invisible lines that space-time has drawn. You can't see those lines, but they are there, drawn by Earth's mass, followed by every falling leaf and every orbiting moon. Though it feels ordinary, it is anything but. Think about this. Every time you jump, even slightly, you are temporarily resisting the gravitational pull of an entire planet. You leave the surface, you fight the curvature of space-time for a breathless second, and then you return, always gently, back to the guidance of Earth. Even astronauts in space are still held by Earth's gravity. The reason they float, weightless, inside the International Space Station is not because they are beyond gravity's reach. They are falling. They are falling toward Earth constantly. But they are also moving sideways so incredibly fast that they keep missing the ground. That's what an orbit is. Falling forever without hitting anything. They are following the curved lines of space-time so perfectly that they remain in a state of perpetual descent. The same is true for the moon, for satellites, for stars and galaxies. They all move through space like fish in invisible currents, guided not by strings or engines, but by the quiet, persistent shape of gravity. And black holes? They are the deepest, fastest currents of all. Their gravity isn't a simple slope. It's a waterfall in the fabric of space-time. Once you cross the edge, the event horizon, there is no way back upstream. Not because something is chasing you, but because the river of space itself has turned vertically downward, and the flow of time itself has been altered within. It is within this curved, flexible fabric that our two black holes perform their dance. Sometimes, across vast distances, two black holes find each other. They drift closer, drawn not by hunger or desire, but by the elegant, mathematical inevitability of curved space. Their individual dimples in space-time begin to overlap. Their gravitational wells merge into a shared landscape. Their motions change and a slow, stately spiral begins. No splash, no bang, just a steady, silent circling for thousands, millions, sometimes billions of years, like two dancers who don't yet know they are a pair, moving to a rhythm set by the cosmos itself. As they move, their accelerating paths create ripples. Tiny, rhythmic waves in the fabric of space-time. Gravitational waves. They are soft, gentle pulses, stretching space in one direction while squeezing it in another. These waves travel outward at the speed of light, carrying the story of the spiral across galaxies. Some of these waves will travel for 100 million years and then pass, utterly unnoticed, through the soft skin of your body. You don't feel them, but they are real. They are the whispers of black holes in motion, messages written in the language of gravity itself. And so, tonight, as you breathe, you are a part of that story. Gravity holds your breath. It holds your heartbeat. It holds galaxies in their slow, spiraling arms. It is both comfort and mystery, the most familiar force and the least understood. So the next time you drop something, or feel the weight of your body settle into sleep, remember, you are moving through curved space. Gravity, quiet as a breath, is drawing you gently home. But if gravity can ripple, if it can whisper across the light years, then what are these waves? Really? How do we hear them? How do we know, from so far away, that two black holes have become one? Let's drift deeper into that mystery. Next, there is a hush in space so deep it feels absolute. But silence does not mean stillness. Even in the deepest quiet, things move, things turn, things draw together. And somewhere, not in a place you could point to on a map, but in the grand, dark deep of the cosmos, two black holes begin their final spiral. They are invisible to your eyes, not because they are hiding, but because they have erased themselves from the visible universe. They are white, not in color, but in their inability to reflect or emit any light. They are voids, but if your mind could paint the universe not in light, but in the contours and curves of spacetime itself, you would watch them circling. Slowly at first, then faster. Not like dancers on a ballroom floor, but more like two whirlpools in a dark sea. Pulling, tightening, growing inexorably closer. This is no chaotic chase. It is a rhythm. Deep, patient, mathematical. Every orbit brings them nearer, and as they spin, they speak. Not in sound, for no one can hear in the vacuum of space, but in waves. Not waves of water or light, but gravitational waves. Imagine a perfectly calm lake, its surface still and mirror-like. Now drop a stone into its center. What happens? Ripples spread out, gently, rhythmically, in all directions. They are the lake's way of remembering the stone's impact. That is what orbiting black holes do to the fabric of spacetime. Their motion disturbs the very shape of the universe. They send out ripples, invisible yet vast gravitational waves. It is a language written not on paper or in light, but into the structure of spacetime itself. Crucially, these waves don't move through space. They are space, stretching and compressing as they travel. Every time the black holes swing around each other, a new wave forms. And each wave carries a message. We are here. We are moving. We are becoming one. Back on Earth, you would never know. The waves that pass through you are unimaginably faint. Their effect smaller than the width of a single proton. But they are real. For a fleeting moment, they bend you just slightly. They lengthen and shrink the distance between the atoms in your body, in your chair, in the planet itself. Then they move on. The black holes have danced, and you have felt the echo, even if you never noticed. As their orbit tightens, the black holes spiral faster. The energy of their frantic motion pours into the fabric of spacetime, and the waves grow louder in gravity's silent language. To us, this louder is not a volume but a frequency, a rising pitch, a chirp. It sounds like the coiling of a cosmic spring, a rising tone that culminates in a final, sharp note. When scientists translate the data into sound waves we can hear, it almost sounds like a bird calling out from the void. But that sound isn't traveling through air. It's not sound at all. It is movement, the movement of space, the whisper of a universe rearranging itself. For decades, this was just a beautiful prediction of Einstein's theory. It wasn't until September 14, 2015, that humanity heard this dance for the very first time. The instruments that made this possible are masterpieces of patience and precision. Their names are LIGO, the Laser Interferometer Gravitational Wave Observatory, and Virgo. LIGO consists of two identical observatories in the United States, separated by nearly 2,000 miles. Each one is an L-shaped cathedral to silence, with arms stretching for 4 kilometers, 2.5 miles, into the distance. Inside these immense vacuum tubes, a powerful laser beam is split in two. Each beam travels down an arm, bounces off a mirror suspended at the end, and returns. In normal circumstances, when the beams reunite, they cancel each other out through a process called interference, and the detector sees nothing. But when a gravitational wave passes through the Earth, it does something extraordinary. It stretches space in one direction and compresses it in the perpendicular direction. For a fraction of a second, one of LIGO's arms gets infinitesimally longer, while the other gets infinitesimally shorter. The two laser beams no longer return in perfect sync. Their perfect cancellation is broken, and a tiny flicker of light, a whisper caught in laser beams, is recorded. The precision required is almost beyond belief. LIGO can detect a change in length 10,000 times smaller than the diameter of a proton. To put that in perspective, it's like measuring the distance to the nearest star, Alpha Centauri, with an accuracy less than the width of a human hair. On that morning in 2015, after decades of design, construction, and upgrades, LIGO was listening. It was listening for nothing. And then it heard something, a ripple, a wave, a whisper that had been traveling for 1.3 billion years. Two black holes, one about 36 times the mass of the Sun, the other 29, had merged in a distant galaxy. The signal was perfect. It was the classic chirp, rising from 35 cycles per second to 250 in less than a fifth of a second before cutting off abruptly as the black holes merged. The final black hole contained 62 solar masses. 3 entire suns' worth of mass had been converted into pure energy, shaking the fabric of space-time in a blast of gravitational waves, all in a fraction of a second. When the wave reached Earth, it stretched and compressed the entire planet, and LIGO's exquisitely tuned arms wobbled in response. It was the first time we didn't just see the cosmos. We felt it. We felt its vibration. The dance was not just theory. It was real, measured, witnessed in the trembling of mirrors and the shiver of space. Since that first detection, we've heard the universe's symphony grow richer. Dozens of mergers have been recorded. Some are from lighter black holes, dancing quickly. Others are from massive, heavy giants, their spirals slow and thunderous. We've even heard the merger of 2 neutron stars, an event that produced both gravitational waves and a spectacular burst of light, allowing us to study the same cosmic event with both ears and eyes. Each signal is a story, a fingerprint. It tells us the masses of the black holes, how far away they were, how long they danced before joining. We are no longer just astronomers. We are cosmic listeners, our ears pressed against the fabric of space-time, hearing the echoes of collisions that occurred when Earth was a world of simple, single-celled life. And the best part? These waves are still traveling. A merger that happened 1 billion years ago might only be arriving at Earth now. It passes through us, through our planet, through the instruments that wait patiently in the deserts of Washington and the forests of Louisiana, and then continues on its way, heading towards stars and galaxies we will never know. Gravity remembers, and it carries that memory endlessly forward. You might wonder, if space can ripple, can it also tear? Can gravitational waves grow so strong they shred the fabric of reality? The answer, as far as we know, is no. The universe is vast, and its fabric is incredibly strong and flexible. Even the most powerful gravitational waves we've detected are gentle, cosmic breaths. They pass through everything, but they do not destroy. They move like a pulse, like time itself, a reminder that the universe is not static, but a living, breathing, dynamic entity. So tonight, as you rest, know that space is still stretching quietly, softly, all around you. Not in chaos, not in fury, but in gentle remembrance of events long past. Two black holes alone, then near, then one. A ripple, a song, a story without light. And you, lying here, are part of that story. You have learned to listen to a language that doesn't need sound, to hear waves that carry memory. And if we follow those waves backward, they lead us to something even more profound. What exactly is this space that ripples? What is this fabric that stretches and carries these whispers so far? What is space-time made of? Let's float into that question next, into the very cloth of the cosmos. Close your eyes for a moment and let your imagination soften the edges of reality. Picture space not as a void, not as a sterile emptiness, but as something with substance. Fabric. Imagine a vast, endless expanse of the softest, most perfectly smooth silk, stretched taut in every direction, dimly shimmering with potential. This is not a perfect metaphor, but it is our gateway to understanding space-time. It sounds abstract, even mystical, but the idea at its heart is beautifully simple. Einstein's great revelation was that space and time are not separate, independent stages upon which the events of the universe play out. They are intimately, inseparably woven together into a single four-dimensional entity, space-time. Everything in the universe, you, me, planets, stars, moves through this connected field. Let's return to the stretched silk in your mind's eye. It is flat, still untouched. Now gently place a marble upon it. What happens? The fabric bends. A small, gentle dip forms around the marble. That dip, that curvature, is gravity. Now roll a smaller marble nearby. It doesn't move in a straight line. It begins to curve inward, following the slope created by the first. Not because the first marble reached out with some invisible force and pulled it, but because the very shape of the landscape, the fabric itself, guided its path. This is the essence of how gravity truly works. It is not a mysterious force pulling at a distance. It is the geometry of the universe. Mass and energy tell spacetime how to curve, and curved spacetime tells objects how to move. It is a quiet, continuous conversation. Here is my mass, says the Earth. Then here is the curve of my fabric, replies spacetime. And here is the path I must follow, answers the moon, gliding effortlessly along the geodesic, the straightest possible line in a curved world. This fabric, this spacetime, is everywhere. It is beneath you right now, curving softly under the weight of our planet, holding you to the floor. It stretches between the Earth and the Sun, keeping us tethered in a warm, life-giving orbit. It allows galaxies to spin in their grand, slow spirals. Right now, this very moment, space-time is beneath you, around you, and in a very real sense, within you. Your very breath flows through this invisible field. Every step you've ever taken has bent it, just slightly. Even you, with your mass, press into the fabric of space-time, leaving the smallest, softest of dents. Now think again of that stretched sheet. What happens if you place something truly massive upon it? Planet makes a small valley. A star creates a deeper, more pronounced well. But a black hole is different. It doesn't just make a dip, it creates a puncture. A pit so infinitely deep and steep that the fabric curves all the way back in on itself. Nothing, not even light, can climb out. Not because light is too weak, but because the very shape of space has turned vertically downward. There is no out anymore. All paths lead inward. This is why black holes are invisible. Not because they are hidden in shadow, but because the paths light would need to take to escape simply no longer exist. But even black holes do not tear the fabric. They bend it, they stretch it, they deepen it to an extreme. And when they move, when they orbit one another, for instance, they send out waves in this cosmic cloth. Gravitational waves. You've already felt them in our stories, in the chirps heard by LIGO. They are not sounds in the air, but movements in the very structure of existence. The fabric flexes, it recovers, and the wave continues on its journey. Space-time is elastic, not like rubber, but in the way water is able to flow, to ripple, to carry motion across great distances. It is a softness with a firm structure. It is strong enough to hold galaxies in place for billions of years, yet sensitive enough to ripple with the whisper of two colliding black holes a billion light-years away. It is the most delicate strength you can possibly imagine. This idea of a fabric of reality may feel like a metaphor, but to scientists, it is as real as the ground beneath your feet. It makes predictions. It explains how light from distant stars bends as it passes our sun. It tells us why time slows down near massive objects. It is so real, so tangible in its effects, that the GPS in your phone must account for the curvature of spacetime around the Earth to give you accurate directions. Without these tiny corrections from Einstein's theory, your phone's map would be wrong by hundreds of feet within minutes. So, when you walk outside and look up at the stars, you are not just looking into a distant emptiness. You are gazing across a structure, a quiet, invisible architecture that holds everything in place. That star shining faintly in the night, its light has traveled for years along the gentle curves of spacetime, bent slightly by the gravity of every star and galaxy it passed, carried steadily toward your eyes. Its path was not straight, but it was graceful, shaped by the mass it encountered. And your path, too, has been shaped by this cloth. Every fall you've taken, every leap for joy, every orbit around the sun, every drift into sleep, all of it has been guided by the gentle, persistent curves drawn in the spacetime beneath your feet. You are moving through spacetime right now, even as you lie perfectly still, even in sleep, because time itself is a part of this fabric, and you are always moving forward through it. It is comforting, in a way, to know that space is not nothingness, that time is not just a ticking clock, but that together they form something soft, something shaped, something that holds you. You are not floating in a void. You are resting in a web of gentle structure, woven from gravity and geometry. And black holes? Those strange, quiet wells? They are simply the deepest dimples in that web. Places where spacetime has curled so intensely in on itself that it has folded inward, keeping its secrets forever. So, the next time you close your eyes and feel a sense of stillness, remember, stillness is relative. You are moving through time, through space, through the slow, curved fabric that wraps the stars. A fabric that remembers every mass, every moment, every ripple. And if this fabric can hold stars and carry waves of gravity, can it also hold something else? Information, memories, the stories of all that has ever fallen into a black hole? Because if a black hole swallows everything, where does it all go? Do the things it consumes disappear forever? Or does the universe, in its infinite wisdom, find a way to remember? Let's wonder about that next. You have followed the story this far. A star lived, blazed with light, and then collapsed, becoming something strange and silent. A black hole. Now, a new question arises, quiet but clear in the stillness. Can we see it? The answer, like so many in the universe, is both simple and deeply mysterious. No, you cannot see a black hole directly, but yes, you can see what it does. A black hole gives off no light of its own. It does not glow. It does not reflect. Once something crosses its boundary, the event horizon, it vanishes from the viewable universe. Its light is pulled inward, forever. So how do we know with certainty that they are really there? Because gravity leaves a trail, curves paths, it bends light, changes motion. In the world of astronomy, these tiny shifts and swirls are how we see the invisible. Imagine walking through a quiet forest. You never see the elusive animal itself, but you see the evidence of its passage. Broken branches, footprints in the soft soil, a ripple of movement in the undergrowth. You don't need to see the creature to know it is real, that it passed this way. Black holes leave the same kind of marks on the universe around them. One of the earliest and most compelling signs came from a system called Cygnus X1. Astronomers observed a brilliant blue supergiant star. But something was wrong. This star was not moving in a calm, straight line. It was wobbling, tugged in a tight, fast orbit around nothing. It was as if it were tethered to an invisible, massive companion. No second star could be seen, yet from that point of nothingness, intense X-rays poured out into space. What we were witnessing was a star orbiting a black hole, and the black hole was feeding. The X-rays were the final, fierce scream of light from gas being torn from the star and heated to millions of degrees as it spiraled into the accretion disk before vanishing. When a black hole is surrounded by gas, that gas doesn't fall straight in. It spirals, drawn by gravity, compressed and heated by immense friction to temperatures of millions of degrees. Just before it crosses the event horizon, it glows with incredible intensity, emitting torrents of X-rays and other radiation. This glowing, swirling maelstrom is an accretion disk, a final, brilliant testament to matter on the brink of oblivion. While we can't see inside the black hole, we can see this ring of fire just outside it. But black holes reveal themselves in an even more ghostly way. They bend light itself. They don't just pull it in. They curve its path around them. This effect, called gravitational lensing, is a bending of light's trajectory by the curvature of spacetime. It's as if the black hole were a magnifying glass made of pure gravity, distorting the images of stars and galaxies that lie behind it. Sometimes, when the alignment is perfect, this creates beautiful, perfect rings of light known as Einstein rings. They are one of the most beautiful and conclusive clues that something massive and unseen is present. So no, we cannot take a photograph of a black hole itself, but we can take a picture of its shadow. And that is exactly what we did in 2019. The Event Horizon Telescope, EHT, was not a single telescope. It was a feat of global cooperation, a virtual telescope the size of the Earth itself. By synchronizing radio observatories from the high deserts of Chile to the frozen plains of Antarctica, from the mountains of Hawaii to the peaks of Spain, astronomers created a planet-sized dish, an instrument with a resolution sharp enough to read a newspaper in New York from a sidewalk cafe in Paris. Their target was a supermassive black hole at the heart of a giant galaxy called Messier 87, 55 million light-years away. For nights in April 2017, these telescopes stared, unblinking, at the same point in the sky, collecting waves of light that had been traveling for 55 million years. The result, revealed 2 years later after painstaking analysis, was not sharp. It was not colorful. It was grainy, fuzzy, and beautiful. It showed a brilliant, asymmetric ring of fire, the photon ring, and at its center a dark circle. That dark center was not the black hole itself, but its shadow, the silhouette of its event horizon. It was the absence of light that revealed the presence of the ultimate absence. It was proof not just of a theory, but of the thing itself. The image circled the globe. A dark circle, ringed in flame, not an eye, not a hole, but something deeper. A presence that said, "Yes, I am here. You cannot see me, but you can see what I do to the light around me." And perhaps for now that is enough. Seeing a black hole is like seeing the wind. You don't see the wind itself, but you see the sway of the trees, the rustle of the leaves, the dance of branches. Black holes sway stars. They rustle light. They bend time. And when we pay close attention, we see them by their profound influence. Even in our own galactic home, we have seen this dance. At the center of the Milky Way, hidden behind thick clouds of dust, lies a black hole named Sagittarius A star. We cannot see it with optical telescopes, but we have watched stars orbit it. One star, called S2, completes a frantic 16-year orbit around the invisible point. Swinging closer to the black hole than Pluto is to the Sun, moving at speeds in excess of 15 million miles per hour. We have measured its path, its speed, its acceleration. And from that, we know with utter certainty, there is a black hole there. A supermassive one, 4 million times the mass of our Sun. And it is dark, utterly, perfectly dark. But it pulls, and that pull is visible. So perhaps the lesson is this: not everything that is real needs to be seen directly. Some things are known by their effects, by their gravity, by the way they change the world around them. Black holes are like this, quiet, invisible, but undeniable. As you rest now, you can imagine that dark circle, ringed in light, pressing into the fabric of space. You won't see it in the sky tonight, but it is there. And in a strange, poetic way, it sees you, not with eyes, not with thought, but with gravity, with presence, with the soft, silent influence that only the most powerful things in the universe possess. But seeing is just the beginning, because that black hole in M87 and the one at the heart of our own galaxy don't just exist. They shape, they hold stars together, they anchor entire galaxies. Could it be that black holes are not just endings, but centers? Not just destroyers, but architects? Let's turn our gaze to that idea next, to the quiet giants beating at the heart of every spiral arm and starlit world. There are moments in science that feel less like discovery and more like revelation. Moments that transcend equations and data, touching something deeply human, something quiet and vast. In April of 2019, the world was gifted one of those moments. A blurry, amber-hued ring, a shadow, an image that didn't just confirm a theory, but made the invisible tangible. It was our first direct glimpse not of a black hole itself, but of the void it carves in the light, its shadow. A shape defined not by presence, but by a profound, silent absence. This particular black hole, a behemoth named M87*, lives in the heart of a galaxy far, far away, Messier 87, some 55 million light-years distant. It is almost unimaginably enormous, weighing in at over 6.5 billion times the mass of our Sun. For decades, astronomers had suspected its existence. They had seen the evidence. Colossal jets of subatomic particles shooting thousands of light-years into intergalactic space from the galaxy's core, beams of power that could only be launched by something with the mass and spin of a supermassive black hole. But suspicion is not sight. It was only with the creation of a planet-sized eye, the Event Horizon Telescope EHT, that we could finally look directly into the heart of the darkness. The EHT was a miracle of coordination and technology. It was not one telescope, but many, a global network of radio observatories spanning from the high, dry Atacama Desert in Chile to the frozen plateau of Antarctica, from the volcanic peaks of Hawaii to the mountains of Spain. Synchronized by the flawless pulse of atomic clocks, they acted as one single, Earth-sized instrument. For several nights in April 2017, they collectively stared, unblinking, at the core of M87, gathering not the light our eyes can see, but the longer, quieter waves of radio light. 2 years of painstaking analysis later, they gave us the picture. It was soft, grainy, and breathtaking. A fiery, asymmetrical ring of light, the photon ring, where light is trapped in a final, dizzying orbit, and at its center a dark void. The shadow. This wasn't a shadow in the traditional sense, as if an object was blocking a light source. This was the silhouette of a place where light itself could no longer escape. It was an echo of the event horizon, a negative image of the ultimate positive gravity. What made this image so profound wasn't just its confirmation of a century-old theory, though it did that perfectly. The near-perfect circle matched Einstein's predictions with stunning accuracy. It was the sheer, haunting presence of it. You stare into that darkness, and in a strange way it stares back, not with menace but with a still, ancient power. It is not a thing you could touch. It is a place where gravity has rewritten the rules of reality, where time slows to a crawl, light bends into circles, and the future is sealed. And yet, around this place of ultimate stillness, there is a maelstrom of motion. Gas swirls at nearly the speed of light, heated to billions of degrees. Magnetic fields of unimaginable strength twist and snap. Photons dance on curved paths, some escaping to form the fiery halo we see, others vanishing forever. It is a universe of paradox. Fury outside, perfect stillness inside. A glowing crown of energy surrounding a perfectly black, silent heart. The EHT captured more than an image, captured a principle, a diagram of extreme gravity made real, and it was deeply personal. We didn't build this global endeavor just to tick a box in a textbook. We built it because we, as a species, needed to see. We needed to look into the heart of this cosmic mystery and say, with the full weight of our collective curiosity, there you are. And when the image was released, something remarkable happened. The world paused. Not just scientists and astronomers, but people everywhere. They looked at that fuzzy, fiery ring and felt something ancient stir within them. A sense of scale, of wonder, of humility. Even in its blurriness, it told a story that in the vastness of space, there are places where physics as we know it ends, where matter surrenders completely to gravity. And we, with our fragile bodies and brilliant minds, can still find them. Perhaps the most poetic part of all is the age of the light that formed that image. The radio waves that were captured by our mountaintop dishes had been traveling for 55 million years. They began their journey when Earth was a world of dinosaurs, passed by stars that have long since died, floated through clouds of cosmic dust, and were finally, tenderly, caught by our machines. We reached across 55 million years of time and held a shadow in our hands. But that black hole M87** is not a solitary anomaly. It turns out that these silent giants are not the exception, but the rule. They live at the heart of nearly every large galaxy we have studied. Our own Milky Way has one. Why? What is the connection between the darkest objects in the universe and the brightest collections of stars? Let's drift closer to home, to the spiral arms and glowing core of our own galaxy, to understand the role of these quiet anchors. Galaxies spin. This is a fundamental truth of the cosmos. Spiral arms, like those of our Milky Way, unfurl with a slow, majestic grace, sweeping through space over hundreds of millions of years. Stars twirl in elegant arcs, and vast clouds of gas and dust drift in their gravitational currents. From a distance, a galaxy looks like a whirlpool of starlight, a pinwheel of cosmic fire. But if you could travel inward, past the spiral arms, past the bustling stellar neighborhoods, into the crowded, brilliant core, you would find something unexpected. Not a brighter and brighter concentration of stars, but a place where the light gives way to stillness, a silence. You would find a supermassive black hole. These central black holes are a different breed from the stellar mass black holes born from dying stars. They are millions, even billions of times more massive. Yet, for all their immense weight, they are incredibly compact. Their gravity is folded into a point of infinite density, hidden behind an event horizon. You might think such a monstrously heavy object would tear its host galaxy apart. But the opposite is true. It organizes it. It helps shape the galaxy around it, not through active pushing or pulling, but simply by existing. Its immense mass creates a deep, stable gravitational well, the hub of the galactic wheel, the still center of the turning dance. At the very center of our Milky Way, hidden behind thick veils of interstellar dust, there is a black hole named Sagittarius. We cannot see it with optical telescopes, but we have mapped its presence with exquisite precision using radio and infrared eyes. We have watched stars orbit it. One star, known as S2, follows a long, oval path that brings it breathtakingly close to the black hole, moving at a blistering 3% of the speed of light at its closest approach. A speed dictated by the pull of an invisible object about 4 million times the mass of our Sun, all confined to a region of space no larger than our solar system. And yet, for all its power, Sagittarius A* is quiet. It is not actively feeding. It is not surrounded by a raging, brilliant accretion disk. Sits not asleep, but in a state of calm. It is a dormant giant, a fireplace where the last embers glow faintly beneath the ashes. It waits. This reveals a surprising truth about supermassive black holes. They are not always active monsters. They can be patient, quiet custodians. They hold the stars of the galactic center in their intricate orbits, shaping the overall structure of the galaxy. Their gravitational influence is the unseen hand that keeps the spiral arms from flying apart, that gathers stars into the central bulge. Which came first, the galaxy or the black hole? It is one of the most humming, active questions at the frontier of astrophysics. The evidence we have suggests a coevolution, a cosmic companionship that began in the infancy of the universe. The mass of a galaxy's central black hole is often closely correlated with the mass of the galaxy's central bulge of stars. It is as if the black hole and its galaxy have been in a slow, billion-year conversation, growing together, shaping each other, each influencing the other's destiny. Some of these black holes formed when the universe was less than 1 billion years old, a puzzlingly short time for such behemoths to grow. We see their evidence in the form of quasars, incredibly bright, active galactic cores powered by voraciously feeding supermassive black holes, shining from the very edges of the observable cosmos. Their existence tells us that black holes were not just the end products of stellar evolution. They were part of the cosmic foundation, present at the beginning of galactic history. Perhaps they helped galaxies form, providing a gravitational seed around which the first stars could gather. Or perhaps they grew with astonishing speed inside the first proto-galaxies. What we know with growing certainty is that these dark hearts are not passive residents. They are active participants in the life of their galaxies. When they feed, they can send out powerful winds and jets of radiation that regulate the formation of new stars, heating up or blowing away the gas that would otherwise collapse into stellar nurseries. Too much activity, and star formation is suppressed. Too little, and the galaxy may age into a cold, red stillness. It is a delicate billion-year feedback cycle, a quiet gravitational balance maintained by the darkest object in the galaxy. So tonight, as you rest beneath the slow, grand swirl of the Milky Way, know this. There is a black hole spinning at the center of our galaxy. You will never see it. You will never feel its pull directly, but it is there, holding everything in place not with violence, but with immense, patient gravity. It is not eating your galaxy. It is anchoring it. It is the silent architect of the beautiful spiral you are a part of. It is a profound paradox, that something invisible, something that erases light, could also be the quiet, ordering principle behind so much cosmic beauty. But that is the lesson of black holes. They are both destroyers and creators. They are the end of one story and the beginning of another. They teach us that not all power is loud, that stillness can be immense, and that gravity alone can build wonders. When you next see a photograph of a galaxy, its arms stretched like stardust across the black velvet of space, remember the center. Remember the silence. Remember the black hole you cannot see. It does not shine, but without it, the stars would drift, the beautiful shape would slowly fade, and the galaxy would lose its form. And perhaps now, as you lie there, a new wonder arises. If black holes grow so large and live so long at the centers of galaxies, what happens when two galaxies meet? Do their black holes meet, too? Do they find a partner in the vast dark and begin their own final dance? Let's drift into that question next and watch the slow, stately spiral of an inevitable cosmic union. In the deep quiet of space, nothing seems to rush. Stars turn on their axes with stately slowness. Galaxies stretch across the void, their motions measured in hundreds of millions of years. Black holes drift like shadows in a dark room. Everything moves, but it moves with the patience of time itself, a slowness that can make eternity feel tangible. And yet, even this profound stillness has a direction. Even silence can lean toward something. This is the story of black holes that do not remain alone. Most black holes begin in solitude. Born from the collapse of a single massive star, they sit in the dark of interstellar space, pulling gently on whatever dust, gas, or unlucky star wanders too close. But some, especially the supermassive giants at the centers of galaxies, are not destined for a life of isolation. Because galaxies themselves are not static. They orbit within clusters, they sway in the gravitational currents of the cosmos, they drift, and sometimes they collide. The word collide can be misleading. It conjures images of a cosmic car crash, a violent, fiery smash. But that is not the way of galaxies. Galaxies are mostly empty space. They contain billions of stars, yes, but the distances between those stars are immense. When two galaxies merge, it is not a smash but a slow, graceful dance, a weaving of stars and dust, a gentle pulling of spiral arms, a bending of motion that unfolds over billions of years. From our distant vantage point, it is one of the most beautiful sights in the universe. Two spirals becoming tangled, their structures dissolving into a new, often elliptical, shape, with long, luminous tidal tails of stars thrown outward like glittering streamers in the cosmic dark. And at the heart of each galaxy, a supermassive black hole. When galaxies begin their merger, these central black holes are initially far apart, separated by tens of thousands of light years. They are each the king of their own castle. But as the stars and dark matter of the two galaxies swirl and mix, as orbits are reshuffled in a grand gravitational reorganization, a slow, inevitable process begins. The two black holes, the heaviest objects in the new, combined system, begin to sink. Drawn by dynamical friction, a kind of gravitational drag from the surrounding stars, they drift toward the common center of the new, larger galaxy. It is a process of immense patience. It can take 1 billion years or more for them to even notice each other directly. They are like two mighty ships, each caught in the same vast, slow-motion whirlpool, gradually drawing closer with each circuit. But once they do get close enough to feel each other's gravitational influence, within a few light years, the final act of their dance begins. This is the part we have been waiting for, the binary spiral on a supermassive scale. At first, they orbit each other, two invisible titans waltzing in the crowded stellar core. They transfer energy to the surrounding stars, kicking them out into wider orbits, which allows the black holes to spiral even closer. This is a slow, stately tightening. Then, as the space between them narrows to less than a light year, a new force takes over, the emission of gravitational waves. Just like their stellar mass cousins, these gigantic black holes, as they orbit, stir the space-time around them, sending out ripples. These waves carry away orbital energy, causing the black hole's paths to tighten further, their dance to accelerate. The spiral becomes a fall. The fall becomes an embrace. Why do they merge? Why not just orbit each other forever? The universe, in its elegant economy, does not allow for perpetual motion. Every orbit carries kinetic energy. To merge, to come to rest as a single object, that energy must go somewhere. In the final stages, gravitational waves are the universe's release valve, carrying the colossal energy of the inspiral away into the cosmos. You could imagine it like two whirlpools in a river, separate at first, but caught in the same current. The spiraling water around each one interacts, pulling them together. Eventually, they merge into a single, larger, more powerful whirlpool, their identities consumed by a new, unified structure. These galaxy-scale mergers are not rare accidents. We believe they are a fundamental part of cosmic evolution, a primary way supermassive black holes grow to such immense sizes. One black hole finds another. They merge. That new, larger black hole may, in another few billion years, meet another. A cosmic cycle of quiet, immense unification. We look for the signs of these impending unions. Sometimes we see two bright, active galactic nuclei close together, each flickering with the X-rays of a feeding black hole, a sure sign of two galactic cores nearing their end. Other times we see galaxies with bizarre, distorted shapes, the telltale signs of a gravitational tug-of-war. And in the future, we will not just see them, we will hear them. The gravitational waves from merging supermassive black holes are too low frequency and long period for LIGO to detect. They are a deep bass note to LIGO's high chirp. To hear them, we need to go to space. Projects like the Laser Interferometer Space Antenna LISA, a planned mission by NASA and the European Space Agency, aim to do just that. Imagine 3 spacecraft, millions of kilometers apart, flying in a perfect triangle, connected by laser beams. They would form a gravitational wave observatory with arms far longer than any possible on Earth, tuned to the low-frequency rumble of the universe. LISA would be able to hear the final millennia of the dance between supermassive black holes, the slow, rising crescendo that culminates in the most energetic events since the Big Bang. So tonight, imagine 2 such black holes. One was born in a spiral galaxy, the other in an elliptical. They drifted for eons, unaware of each other's existence. They circled in the silence of their own domains. Now, drawn together by the merged gravity of their combined galaxy, they move as one, invisible to any eye, but impossible to stop. You don't need to rush. They don't. Their spiral takes its time, but its end is as inevitable as gravity itself. And when it comes, it will send a tremor through space-time that will outlast the stars. But this grand external dance leads to an even deeper, more perplexing internal question. As they merge, as their event horizons touch and flow into one another like 2 drops of water, what happens to what's inside? What happens to the stars they have consumed, the particles, the photons, the very information that crossed their thresholds? Does a black hole ever reveal its secrets? Or does it forget truly and utterly? Let's float gently and humbly toward that mystery next, to the edge of physics itself. There are questions that science can approach, measure, observe, and test. And then there are questions that hang like stars just beyond our reach, visible but distant, real but wrapped in a shroud of mystery. The question of what happens inside a black hole is one of those. It is a whisper at the very boundary of our understanding, a frontier we know is there but cannot cross, not even in our imagination, without our maps of reality beginning to fold and tear. Still, tonight we can drift close to the edge. We can look into the darkness and wonder. You remember the event horizon. It is the surface of no return. It is not a physical wall, not a hard shell you could bump into. It is a region in space, a mathematical boundary defined by gravity's ultimate victory over light. If a particle of light, a photon, crosses it, it can no longer climb out. Its future, from that moment on, lies inexorably inward. If time itself could be said to have a direction, it too bends inward at this threshold. From the outside, the event horizon presents a strange and ghostly spectacle. Imagine watching an astronaut, brave and foolish, falling toward a black hole. From your safe, distant perspective, you would see something bizarre. As they approach the event horizon, their signals would slow down. Their clock would appear to tick more and more slowly. Their image would stretch and redden, fading to a dim crimson smear. They would appear to slow, to freeze, suspended forever just at the threshold. Their image etched onto the horizon for all time before eventually fading to black as their light becomes too dim and redshifted to see. To you, the outside observer, the fall never truly concludes. It is a journey that asymptotically approaches an end, but never, from your viewpoint, reaches it. But from the falling astronaut's point of view, the story is starkly different. There is no sudden jolt, no dramatic line to cross. They would drift through the event horizon without any local sensation, any flash or bang. It is an invisible threshold. But from that moment on, every possible path, every future, leads inward toward the center, the singularity. There is no turning back. Not because a force is holding them, but because the very geometry of spacetime has become so warped that out is no longer a direction that exists. That center, the singularity, is not a place in any way we can comprehend. It is a point where our current laws of physics, the very equations of general relativity, break down. Density becomes infinite, space-time curvature becomes infinite. It is not that we've hit a wall. It is that the road ends and the map turns to nonsense. Our understanding of reality dissolves into a shower of infinities. We don't know what happens there. Some theories suggest that the rules of quantum mechanics, which govern the very small, might smooth out this infinity into something else. A Planck scale structure, a fuzzball, a something still mysterious but not infinite. Others believe an entirely new theory of quantum gravity, one that unites Einstein's relativity with quantum mechanics, is needed to explain it. But for now, the singularity remains the ultimate "here be dragons" on our cosmic map. Here is something even stranger. Inside the event horizon, the roles of space and time seem to swap. Outside, you can move freely in space but are carried inexorably forward in time. Inside, the radial direction toward the singularity becomes more like time itself. You don't fall through space. You are carried into the future, and that future, in the grim geometry of the black hole, ends at the singularity. No matter how you twist or turn, it is your future that draws you there. Your path is not just physical, it is temporal. This leads to one of the greatest conundrums in modern physics, a paradox that has divided theorists for decades: the information paradox. You see, quantum mechanics, the other pillar of modern physics, has a fundamental rule. Information cannot be destroyed. Information, in this sense, is the complete specification of a system, the position, momentum, spin, and type of every particle. Quantum mechanics says this information can be scrambled, transformed, made incredibly difficult to read, but it can never be truly erased. It is a law of conservation, like the conservation of energy. Black holes, however, seem to be the ultimate shredders. Once something crosses the event horizon, all the intricate information about what it was, whether it was a diamond, a book, or a hapless astronaut, seems to be lost forever. All that remains, from the outside, are three simple properties: mass, electric charge, and spin. This is known, poetically, as the no-hair theorem. A black hole has no hair, no frizz, no details, no individuality beyond these three numbers. It is the ultimate simplification, So where did the information go? Is it truly destroyed at the singularity, violating a cornerstone of quantum mechanics? Or is it somehow preserved? This is the information paradox. Stephen Hawking famously thought that information was lost, which would require a fundamental rewrite of physics. This sparked a decades-long debate. Today, many physicists lean toward the idea that information is, in fact, preserved. But how? Some of the leading ideas are mind-bending. The holographic principle suggests that all the information about what fell into a black hole is not lost inside, but is somehow encoded on the two-dimensional surface of the event horizon, like a cosmic hologram. The three-dimensional interior is a projection of this information stored on its boundary. Another idea is that information slowly leaks back out, scrambled into randomness, through the very faint Hawking radiation that black holes are predicted to emit. We don't know the answer. Black holes force us to confront the limits of our knowledge. They are not just objects. They are edges. Edges of physics, edges of thought, edges of understanding. But perhaps that is what makes them so compelling. Not just their gravity, but their mystery. They remind us that the universe does not owe us easy answers, that some truths are wrapped in deeper truths, that we can come right to the precipice and still not see the bottom. So tonight, as your breath slows and your thoughts drift inward, imagine the inside of a black hole, not as a place of destruction, but as a place of ultimate depth. Not as darkness, but as a question. A place where the rules dissolve, where motion becomes time, where endings are beginnings folded in upon themselves. You cannot go there. You cannot come back. But still it exists. And the fact that such a place exists, hidden in the quiet centers of galaxies, is enough to stir a profound and lasting wonder. It means the universe has corners untouched by our certainty. It means we still have mysteries to fall into. But one final question waits in the deepening night. If black holes take in and hold so much, do they ever let anything go? Do they grow forever, or do they, too, one day come to an end? Let's float gently there, next, to the slowest, quietest loss imaginable, to the final, patient breath of a black hole. Black holes grow. This much seems certain. They feed on stray gas, on wayward stars, on entire companion black holes if they drift too near. When they merge, they don't cancel each other out. They add up. They become something larger, heavier, a deeper well in the fabric of space-time. Growth seems to be in their nature. A natural conclusion, then, might be to imagine them growing forever, becoming larger than galaxies, larger than galaxy clusters, an endless, dark sink at the center of reality, consuming everything given enough time. But to answer whether this is their ultimate fate, we must drift into the truly long life of a black hole. We must watch it not only feed and merge, but also wait, and ultimately change. Let's begin with growth. A black hole born from a collapsing star might be only 10 or 20 times the mass of our Sun. But if it resides in a dense cluster or the gas-rich center of a galaxy, it can begin to accrete, to pull in matter. This process is not a silent plunge. The matter, governed by the conservation of angular momentum, spirals in, forming a brilliant, furious accretion disk. It heats up, radiates X-rays, shines with immense energy as a final testament before it disappears over the event horizon. This glow is how we find many black holes, not by seeing the dark thing itself, but by the light of its final feast. There is, however, a limit to this gluttony. If a black hole tries to pull in matter too quickly, the intense radiation pouring out from the hot inner disk actually pushes back on the infalling gas, blowing it away. This balance is known as the Eddington limit, a kind of natural speed cap on black hole growth. It doesn't stop the growth, but it regulates it, ensuring it is often a slow, stately process over millions of years. Then there are the mergers, as we've discussed. A 30 solar mass black hole and a 40 solar mass black hole might become a single 68 solar mass hole, with 2 suns' worth of mass converted into the pure energy of gravitational waves. This is how we think the supermassive black holes in galactic centers were built. Not all at once, but step by step, merger by merger over the lifetime of the cosmos. And so they grow. Some to billions of times the mass of our sun, quiet giants holding whole galaxies in their gravitational sway, heavy beyond comprehension, yet invisible to the eye. But even these titans do not grow forever. Eventually, they run out of fuel. The nearby gas is consumed or blown away. The stars settle into stable orbits. Other black holes are too far away to merge with, and so they rest. The universe contains many such dormant black holes. They have eaten what they can, and now they wait. They are not dead, just inactive, still capable of flaring to life should a star or gas cloud wander too close. It may take millions of years for such an event to occur, a brief breaking of the silence before the stillness returns. But there is another way a black hole changes over cosmic time. Not through growth, but through loss. A whisper, a fade, a process so slow and subtle that for most of the universe's history, it was thought impossible. This revolutionary idea came from Stephen Hawking. In a brilliant stroke of intuition, he realized that black holes are not quite black. By applying quantum theory to the very edge of the event horizon, he discovered that black holes should, in fact, radiate. This process, now immortalized as Hawking radiation, allows black holes to slowly, imperceptibly, leak energy back into the universe. How can this be? The vacuum of space, according to quantum mechanics, is not truly empty. It is a seething, frothing sea of virtual particles. Particle-antiparticle pairs constantly blink into and out of existence, borrowing energy from the universe for a fleeting moment before annihilating each other and paying the energy back. This is happening everywhere, all the time. Now, imagine this happening right at the event horizon. In a fiendishly clever bit of physics, one of these virtual particles can fall into the black hole, while its partner escapes into outer space. The escaped particle, now real and unable to annihilate with its partner, carries away a tiny amount of energy. And where does that energy come from? It is borrowed from the mass energy of the black hole itself. So, a black hole slowly loses mass by radiating a faint, thermal glow of particles. It is not a fire, not a blaze. It is the slowest possible trickle, a soft, near-eternal exhalation of energy back into the cosmos. The rate of this evaporation is inversely related to the black hole size. The smaller the black hole, the hotter it is and the faster it radiates. A black hole with the mass of a small mountain might radiate away all its energy in a flash, over a time span much shorter than the current age of the universe. But a black hole of stellar mass? It would take far, far longer than the 13.8 billion year age of our universe to evaporate even a tiny fraction of its mass. A supermassive black hole? The timescales become truly astronomical, on the order of 10 to the power of 100 years or more, a number so vast it defies all human intuition. Still, Hawking's idea was profound. It told us that black holes might not be eternal, that even the darkest, most permanent-seeming structures in the universe are, on the grandest scales, transient. They too will one day fade. So we arrive at an answer, not simple but quiet and profound. Black holes grow, they merge, they feed, but they also wait. And in the farthest, coldest stretches of time, when the stars have long since burned out and the galaxies are dark, they begin to fade. Not from an explosion, not from a dramatic decay, but from a long, slow release of quantum breath into the ever-expanding cold. Imagine it. Trillions upon trillions of years from now, in the dark era of the universe. The last stars are dead cinders. The galaxies have evaporated. Only black holes remain, the last macroscopic structures in a cosmos growing cold and dark. And then even they begin to go, one by one, a whisper at a time. They release their mass, their curvature, their story, back into the universe as a faint bath of radiation. The smaller ones go first in a final, bright flash. The supermassive ones persist the longest, glowing with a temperature only slightly above absolute zero. It is the softest kind of ending, not a destruction but a return, a dissolution. Black holes do not rage against the dying of the light. They simply exhale, and the space they once curved so violently becomes still once more. And what happens after that? If black holes fade and ordinary matter is gone, what is left? Only an ever-expanding, ever-cooling emptiness, populated by a sparse sea of photons and subatomic particles, their energy stretched to near nothing by the relentless expansion of space. A universe of memory, but not of substance. A quiet, final chapter. And yet, for all its power, Sagittarius A* is quiet. It is not actively feeding. It is not surrounded by a raging, brilliant accretion disk. It sits not asleep, but in a state of calm. It is a dormant giant, a fireplace where the last embers glow faintly beneath the ashes. It waits. This reveals a surprising truth about supermassive black holes. They are not always active monsters. They can be patient, quiet custodians. They hold the stars of the galactic center in their intricate orbits, shaping the overall structure of the galaxy. Their gravitational influence is the unseen hand that keeps the spiral arms from flying apart, that gathers stars into the central bulge. Which came first, the galaxy or the black hole? It is one of the most humming, active questions at the frontier of astrophysics. The evidence we have suggests a coevolution, a cosmic companionship that began in the infancy of the universe. The mass of a galaxy's central black hole is often closely correlated with the mass of the galaxy's central bulge of stars. It is as if the black hole and its galaxy have been in a slow, billion-year conversation, growing together, shaping each other, each influencing the other's destiny. Some of these black holes formed when the universe was less than 1 billion years old, a puzzlingly short time for such behemoths to grow. We see their evidence in the form of quasars, incredibly bright, active galactic cores powered by voraciously feeding supermassive black holes, shining from the very edges of the observable cosmos. Their existence tells us that black holes were not just the end products of stellar evolution. They were part of the cosmic foundation, present at the beginning of galactic history. Perhaps they helped galaxies form, providing a gravitational seed around which the first stars could gather. Or perhaps they grew with astonishing speed inside the first proto-galaxies. What we know with growing certainty is that these dark hearts are not passive residents. They are active participants in the life of their galaxies. When they feed, they can send out powerful winds and jets of radiation that regulate the formation of new stars, heating up or blowing away the gas that would otherwise collapse into stellar nurseries. Too much activity, and star formation is suppressed. Too little, and the galaxy may age into a cold, red stillness. It is a delicate billion-year feedback cycle, a quiet gravitational balance maintained by the darkest object in the galaxy. So tonight, as you rest beneath the slow, grand swirl of the Milky Way, know this: there is a black hole spinning at the center of our galaxy. You will never see it. You will never feel its pull directly, but it is there, holding everything in place not with violence, but with immense, patient gravity. It is not eating your galaxy. It is anchoring it. It is the silent architect of the beautiful spiral you are a part of. It is a profound paradox, that something invisible, something that erases light, could also be the quiet, ordering principle behind so much cosmic beauty. But that is the lesson of black holes. They are both destroyers and creators. They are the end of one story and the beginning of another. They teach us that not all power is loud, that stillness can be immense, and that gravity alone can build wonders. When you next see a photograph of a galaxy, its arms stretched like stardust across the black velvet of space, remember the center. Remember the silence. Remember the black hole you cannot see. It does not shine, but without it, the stars would drift, the beautiful shape would slowly fade, and the galaxy would lose its form. And perhaps now, as you lie there, a new wonder arises. If black holes grow so large and live so long at the centers of galaxies, what happens when two galaxies meet? Do their black holes meet, too? Do they find a partner in the vast dark and begin their own final dance? Let's drift into that question next and watch the slow, stately spiral of an inevitable cosmic union.